I'm gonna go over worksheet 3, but just the pendulum stuff because our class did the string stuff. So I'm sorry if you needed the string stuff. This is just a long worksheet in general too. So I'm just gonna try to go through things a little quickly, hopefully. And yeah, hopefully it's not too bad. Let's just start off with the graphs. I think this is gonna take up most of our time. It's for a pendulum, so if we imagine our pendulum, right, this is its equilibrium, right, and it's gonna swing back here like so. Let's think about, we're given the position versus time graph. We're really measuring, I think we're measuring the height. I think that would produce this graph. So the height from here. I guess you could also do it for x as well. So it's a very interesting sort of, yeah, let's do it for x. That makes more sense. But yeah, let's just get started. So we're doing x versus t, and we're actually given this graph. So we just got to figure out everything else. So, hey, we know that the slope on a position versus time graph is velocity. So we're really just graphing, for velocity versus time, we're just graphing the slope. So initially, and I think we've done this a lot, right? Slope here is 0, we're going to add in a 0. Slope here is some negative number, we're going to add a negative number. Slope here is 0, slope here is positive, and then slope here is 0 again. So you're going to get your negative sine curve. And if you've taken calculus, this result, cosine and negative sine, you're probably very familiar with. And then we're just going to do the same thing and for acceleration versus time, because on here, the acceleration, or what was I going to say? The slope is acceleration on velocity versus time. So same thinking. It's going to be some sort of negative number, then it's going to be 0. It's going to be a positive number now. It's going to be 0 because the slope, once again, is 0, and then, yeah, negative number right here. You're going to get your negative cosine. And this kind of makes sense because we know that at 1/4 the period, this is when the pendulum is right here. So at that moment, there is no force that is linearly accelerating it because you have your ft, and you have your fg, and ft is bigger because there's a centripetal, centripetal force that is causing circular motion, but there's no force, and I draw this at an angle, but there's no force that's speeding it up for that instant. So it makes sense that at this point, when it's back at equilibrium, the acceleration is 0. So just tying in connections again. I'm going to move on to energy. I think I'll just do energy. I think it's once again something we've done before. Total mechanical energy, it's a constant. We don't, that's obvious. There's no outside forces doing work. For kinetic energy, initially, it's not moving. So I think it makes more, I'll just do it like this. Initially, it's not moving. At 1/4 the time, it's going to be moving very fast. At half the time, it's not moving, right? Because at half the time, it's swung back and is sort of at rest for that moment. At 3/4 the time, it's back at equilibrium. And then obviously the full period, it's back. So you get a sort of cosine graph like this. And we know it's a little flat here because initially, so it's kind of interesting because initially it's not moving. So in the first little second, it's not moving that much, but then right here it's moving a lot more. So it's the curves, really you just got to kind of think through that. But now that we have kinetic energy, you can just do UG as sort of a reflection, in the sense that we know total mechanical energy is constant. So when there's no K, it has to be all UG. When there's no when it's all K, there's no UG. Same thinking. You can make a graph like this. So yeah, there you go. And just a side note, we can say there's no UG because we can pick any height where h is equal to 0. So I can set right here h is equal to 0, and then all the physics works out the same. If you set okay, if this was the floor, right? If you set this is where h is equal to 0, still works. It's just now this whole thing is going to shift it up. You're going to have more total mechanical energy to begin with. It just makes more sense to set this equal to 0. But yeah, let's do the FG tangential. FG tangential in this case is the restoring force. So if you draw your FT, if you draw your FG, the force that is the restoring force is going to be this tangential FGX, right, the tangential component, and then you can draw your same thing right here, FG tangential. So we can see it's flipping directions. Like if we were to, so if we were to if this is like the FG tangential, it's gonna sort of flip directions and point, if it's pointing this way, it's gonna flip directions. So we know that at the very first instant, we have like a bunch of FG tangential pointing, like we can call this like the positive direction, right? It's like pointing down and to the right. And then we're going to have, at 1/4 the time, there's going to be no FG tangential, right? I talked about this. There's going to be no tangential or FG. And then at T, it's going to be opposite direction. And you can get your graph to look like that. And then we can actually figure out it curves like a cosine, a really bad cosine. We can figure out it curves like a cosine because, right, sort of that first instant, it's not moving that much. So it's only going to move like a little bit. So the FG is only going to decrease a little bit. But like right here, it's moving a lot faster. So the FG is going to decrease a lot more. So it's really just thinking it through. But yeah, very similar graphs to what we've been doing. I just wanted to explain this in case the graphs were confusing. Let me see how much time we have. 6 minutes, okay. Not bad. I'll kind of fly through the next one of these for pendulums. We're going to move on to the third one. Second one is some spring stuff. But yeah, I think for the third one, what was it asking? It was asking something about, was it the period is equal to 1? Oh, it's more graphs. Okay, some pendulums and different amounts, and she varies one variable at a time. And we're just sketching with the graphs, and if there's anything we need to linearize, we can do that. So, period versus mass, straight line. For any mass, the period is the same, right? You can get bigger and bigger and bigger mass, you're going to get the same period. Amplitude is pretty similar. So I don't know for amplitude, I'll do maybe theta, like, I don't know, the amount of angle your amplitude. Pretty darn similar. It's going to have no effect. Now, if you're clever, you're probably like, oh, when the amplitude gets really big, you're actually gonna, you might not be straight. Yeah, that's true, but I'm just gonna show that it's a straight line, just because the main idea is that amplitude at small angles, right? In this class, it's not gonna affect period. Let's do period versus length. So, if you remember from your lab, it was a square root. So as a length that's bigger, you just have more t. If you were to linearize that, to linearize a square root, you got to do t squared over L. My mom might be calling me. Yeah? Okay, I'm gonna go soon. But yeah, I'll try to get through the rest of this quick. My parents are just calling me about dinner. So, the slope. Well, we know that t squared is equal to 4 pi squared over g L. Right, this just comes from our equation. If you remember, t equals 2 pi square root L over g. You square both sides. Boom, bada bing. This is our y. This is our x. So we know that this is the slope, right? Y equals mx plus b. Okay, some math stuff. Let's just quickly go over math. And hopefully this mass and amplitude stuff like makes sense, like in terms of explaining it. I won't go too in depth, but yeah, hopefully that's just really a summary from the lab we've done. Let's do the math stuff. So 2 kilogram mass, 3 meter long string. It's pulled back 20 degrees from the vertical. Yep, from the vertical. Determine the period. Okay, T equals 2 pi square root L over G. That's all you need. You don't even need the mass. You don't even need G. So if you do T is equal to 2 pi square root 3 meters over 9.8 newtons per kilogram, I got like something like T equals 3.48 seconds. So yeah, you can try. Now I would try. So obviously you should try every problem first. But for the doubling, so if we want to double the period, how much longer do we need to make the string? So if we want to double the period, So let's do it like this. I don't know how other classes teach proportional reasoning, but yeah. So we want to double the period, and 2 pi is a constant, and then we're gonna. I forget how this works because I don't do proportional reasoning like this. But we want to make this side 2 times bigger. So I think it's like what you have to do 4 over 1, right? So you have to make this the same, but then we have to make this 4 times in order to get 2 is equal to 1 times 2, right? Square root of 4. So the length needs to be 4 times bigger. It's going to be 12 meters, right? Because our initial was 3. Okay, this one's a verbal. It looks like a math one, but it's actually a verbal. 35 kilogram boy and his 70 kilogram dad are swinging next to each other. The boy is going twice as high as the dad, who has a higher frequency. And why? So they both have the same frequency, right? Because just a refresher, frequency is a number of oscillations per second. So if you want to think about a formula, after a period, there's 1 oscillation. So it's just 1 over t, right? Because it's the number of oscillations per second. The t needs to be the same, and t is equal to square root, or t is equal to 2 pi square root L over g, right? They're identical swings, so same like length, and they're on Earth together. Same g. Their periods are going to be the same, so their frequencies are going to be the same. Mass and amplitude do not matter. So just things to remember. All right, calculate the length of a pendulum which has a period of 1 second. So I think if you ever got a question, hey, how long is the pendulum in a grandfather clock? I think this would be the answer, because I think the way grandfather clocks work, they literally like count the number of oscillations, and it's once to 1 second, there you go. So I don't know if that's actually right. I don't know how those are built, but if that's how they work, this is what we're doing. So t equals 2 pi square root L over g, and we need to figure out L when the period is 1 second. I don't want to use a calculator for each step, so I'm just gonna like sort of do a sort of derivation. So 1 second over 2 pi, right? You're gonna get 1 over 2 pi seconds is equal to square root L over g. Square both sides. We get that 1 over 4 pi squared seconds squared. I'm just squaring the units. You don't have to worry about that. Is equal to square root, or not square root, right? Just L over g. Okay, so multiply g by both sides, you get g over 4 pi squared, right? And then this will end up being meters. That's our length. So if you plug this into your calculator, you should get, I got 0.248 meters. And there you go. That's how long a grandfather clock's thingamabob is. Actually, I think it is called a bob. So yeah, there you go, thingamabob. Astronauts on a distant planet set up a pendulum of length L to try to figure out the gravitational field strength G. Derive an equation for G in terms of the length of the string L and the period of a pendulum T. Hopefully this isn't too bad. It's really just deriving. T equals 2 pi square root L over G. I'm going to get at the square root right now. I'm just going to get rid of it so I don't have to worry about it. T squared equals 4 pi squared L over G. And then we're solving for G. So what we can do is actually just multiply both sides by G. And then we got G here. So G T squared equals 4 pi squared L. Divide by T squared. You get G is equal to 4 pi squared L over T squared. So there you go, that's your derivation. Hopefully all of this makes sense. I focus on just pendulums, as you probably figured, so let me know if you want me to go over springs as well. Yeah, thank you for watching, and have a great Friday and a great week. End.